Wednesday's class, and the fifth one is a bonus. So, one that David Carré came up with. Okay, so this is, you imagine you have a conical fiber, and on this fiber you have a drop. Okay, so it's a drop. That's not the best, but you might, right? So you imagine you have this. This is a cone, and you put a drop on it. And the question is, does it go that way or that way, and why? So David asked this question to Pierre Gilles de Gennes, who was his PhD supervisor and Nobel laureate. And de Gennes was scratching his head. So you guys can scratch your heads with the greats. Okay, so let's get going. I like the subject of today's lecture. This is when one looks back at the older previous generation, sort of Lord Rayleigh, Lord Kelvin. They got to solve all these great problems, right? They would look and, for example, we're looking at, and everyone has seen this. You see wind blowing over water. So you have wind blowing over a pond or a river, and you say. Sometimes it's flat, sometimes there are waves, and you want to know what the critical wind speed is to generate waves, and how do you rationalize the size of the waves, okay? So a very simple problem, well motivated. Oh, I should just mention, so again in the first problem, you imagine that the change in surface tension is around 30, okay? So water with alcohol, say, is 40, and water without alcohol is around 70, okay? Okay, so this is a classic problem, and you can basically get at this and all sorts of other things with one formula, formulating one physical problem. So let's do that today. And so the first half we're going to basically solve the math problem, and the second half we're going to try and extract as much physics as we possibly can out of it. So we'll be getting back to drops and bubbles very soon, but this answers the question of where they come from in many cases. So instability of superposed fluids. So we have one fluid over another, and there's going to be relative motion. So we have rho plus over rho minus. We have surface tension at the interface. Otherwise, we, as a feature characteristic of this course, we have Z, X and Z is the horizontal and vertical coordinates. Y is into the board. We have our basic state is shear. So we have uniform velocity below and above, and they're equal in magnitude in opposite directions. So this is U, this is U. And so you can ask, when is this going to be unstable, and what's it going to be unstable to as a function of the system parameters, in particular surface tension, the density difference, gravity. Okay? And there are going to be various limits we can look at. We can look at the case where it's stable. So when we think of wind blowing over water, we think of rho minus being much greater than rho plus. But we can also consider the case, we can also set U equal to 0 and ask, when is heavy stationary fluid unstable when it's placed over light stationary fluid? Okay, and we'll see that it's not always unstable. It is possible to stabilize. Okay. So, through the influence of boundaries, I should say. Okay, so this is our basic state, and then we perturb it. So our perturbed state so it looks like that. So we have some perturbation. We'll call it nu of x y, and t. Okay, and so we want to know which perturbations grow. And this is another example of linear stability theory. We're going to basically imagine all such infinitesimal perturbations, and then we're going to linearize the governing equations in these small perturbations, and then look to see which perturbations grow. So we're going to ask the question, what's the most unstable wavelength? Okay. So let's define the interface. We want to define the interface in the normal. So H so we can define a surface functional. And so the normal okay, so that's our normal, which we're going to need when we calculate the pressure jump across the interface. So our basic state our interface is flat, and we have a velocity field which can be expressed in terms of the gradient of a velocity potential. Okay, so this is our velocity potential. Okay, so we're assuming that viscosity is not important here, so we're looking at potential flow. Okay, so we're imagining the Reynolds number is very high. Certainly is the case when wind blows over water, so viscous effects aren't important. Okay, we can then, so our perturbed field our velocity potential now so we have the unperturbed, and then we have our perturbation field. So phi plus minus. Okay, so if it's a potential flow, so if we can express the velocity as the gradient of a scalar, we know that from continuity, divergence of the velocity has to vanish, so the velocity potential has to satisfy the Laplacian. The Laplacian of the velocity potential has to be 0. Okay, okay, so we have to solve that. Subject to the boundary conditions. 1, the velocity disturbance goes to 0. If if you move far enough from the interface, and then you have the kinematic boundary condition, is simply a statement that the interface moves with the local velocity of the fluid. Okay, where okay, we can linearize the normal. So this is divided by square root of 1 plus nu x squared plus nu y squared. So correct to linear approximation. So we're assuming that all of these things are small. So this is saying this is the z component of the normal, so it's mostly vertical, but there's small perturbations. But these are small relative to this, so we can just linearize this and say correct to linear order, nu x, nu y, 1. Okay, so if we sub now into this, we get okay, so again, we want to linearize. So all of these disturbance variables, so the disturbances from the basic state is order 1, all of the disturbances are order epsilon. When linearizing, we're assuming that the perturbations, so our perturbation fields here are the amplitude and also the variation of the velocity potential. So we assume that these quantities and their derivatives are small. And so we neglect their, whenever we see products of them, we neglect them. So here, for example, this term dies completely. So this would be, and this term is also going to die. Okay? So whenever we see products of these small quantities, we can neglect them. Okay, so then what emerges definitely some instability with this chalk. So it breaks once and it's breaks again in quick succession. Okay, and so we can rewrite this, d phi z equals d nu dt. So this is now the kinematic boundary condition, minus plus 1/2 u d nu dx. Okay? And so this is the kinematic boundary condition. This is true at the interface. So the interface is, of course, on z equals nu. But again, we're assuming these are infinitesimal perturbations, so you basically can just say these boundary conditions apply at z equals 0. Okay, so that's all consistent with the linearization. You're basically saying, again, infinitesimal perturbations, so let's just apply the boundary conditions at 0. Question?
So grad of u equals grad square of...
Hmm?
Shouldn't that be just phi instead of phi plus minus? I'm confused about that.
No? Good. I mean, you have phi is defined above and below the interface, so this... Yeah. So you're solving for two different velocity potentials. Okay, so so the other thing we have to worry about, so this is a little bit technical now, it's just algebra, but then halfway through the class we'll have the dispersion relation, and then we can get a lot of physics out of it. Right? Okay, so the thing we haven't applied yet, but that we know its form, is the normal stress balance, so we know that the jump in normal stress is across the interface, so P minus P plus is given by the curvature, the Laplace pressure, so it's sigma divergence of normal, so of the normal, so we're going to want to evaluate that and linearize. Okay, and again, this is going to be applied at the interface, but we say this is basically z equals 0. Okay, okay, so what are these pressures? How can we, if we know the flow within an inviscid fluid, how can we get the pressure? Bernoulli, anyone? Okay, so okay, and this, so this is a generalization of the Bernoulli theorem, which you all learned in high school. So along a streamline in an inviscid fluid, this is true. So the one that you probably know is this one. But then if you have a time-dependent flow, then this is all true along a streamline. So this can be any function of time. Okay, so here our velocity so we basically take our velocity square of our velocity, which is this thing, the gradient of this thing, squared, so it gives us 1/4 u squared minus plus u, so this is linearizing. So plus higher order terms. Okay, so these are the nonlinear terms which we can neglect. Okay, so if we linearize, so I don't like doing algebra, but this is an example where the algebra is worth it because you get tons of physics out of this analysis. Okay, so this is just a constant, so we can pull this over and throw it in with our f of t, and so we can call this, say, g of t. The point is, this is true above and below the interface, so we're going to subtract one from the other, so the form of this doesn't matter. Okay? Okay. Okay, so we subtract one from the other, and we get the following. Okay, so the pressure difference is given by that, so that we get from Bernoulli, and we know that this is equal to the Laplace pressure. So we're almost there. Okay, so what sorts of solutions do we expect? So this is this is the linearized normal stress boundary condition, right? Okay, so we have the governing equations and we've linearized them. So what kind of solutions do we want to look for? We want to look for waves, right? We want to look for something with a with a given wavelength, and it can have a wave vector in it with any orientation, right? So it's going to be we imagine some perturbation on the interface, but it can have a component in that direction, the wave vector. So, but we want to look to see which wavelength is the fastest growing. So, seek. Okay, so omega determines whether or not it grows, and this alpha and beta are basically the components of the wave vector. Okay, so this is the form of the perturbation, and the velocity potential, the velocity perturbation. I'm going to call it phi 0. So this decays. You can check to see that this is a solution of del squared. This equals 0. So the decays with distance from the boundary, but it also has a wave-like form. All right, because when you take the Laplacian, this pulls down minus alpha squared minus beta squared. This pulls down k squared, and okay, so you have this. It satisfies the harmonic equation. This is harmonic because of this behavior, and we know that it has to decay away from the interface, right? So that's how you pick the signs here. Okay, so we're basically looking for waves. Okay, in fact, this requires this condition. Okay, so we're looking for waves, and we want to know when this is positive. Let's say, when do the waves grow in time, and for which k value is omega maximum. So that's going to be what you see. Right? Okay, so if we apply our kinematic boundary condition, we deduce this. And this gives us minus plus k Okay, and then we're going to sum it to the normal. We're almost there. Our goal is the dispersion relation. So we just have to use a normal stress boundary condition as well. So we're substituting these wave-like forms into the normal stress boundary condition. Get the following. Okay, now we have to sub in, let's call this something else, sub in from here. Okay, so we get this big mess, but this big mess gives us everything we need to know. Okay? Okay, so we get the following. Minus k cubed sigma equals omega Okay, almost there. Okay, so omega, notice we can solve for omega as a function of k from this. Okay? Omega squared plus I alpha u rho minus rho plus rho minus plus rho plus. So we're basically getting a quadratic equation in omega. All right? 1/4 alpha squared u squared plus k squared c naught squared is equal to 0. Okay? So we're getting a quadratic equation. Why does this look so much less awful than that? Because c naught is awful in itself. Okay, so where c naught squared is defined G over K plus sigma over rho minus plus rho plus. Okay. Okay, so this is effectively, this is just a quadratic, so we can solve it. And our dispersion relation, long sought after dispersion relation, which is what one's looking at when one does linear perturbation theory, yields the following. So 1/2 I, and again, all of the physics is going to fall out of this. So tedious as that was, it was worth the effort. Okay. Oh. So okay, where again our wave vector okay, so if you took a course in fluid dynamics and you just got that result, you wouldn't really feel satisfied, right? So, well, what the? So what? You have the answer, but what does it mean? How can we use our answer to try and rationalize our intuition about what happens when wind blows over water or when you have heavy fluid over light, the importance of surface tension? Let's try and get at the physics now. So I'm going to have a 2-minute break while we're sort of we're at the halfway point. I'm going to try and end early today, so I'll just have a couple of minutes break. If anyone wants to grab a water or coffee, go ahead now. I'm going to push on.